Alright guys, so in this video, we're going to be tackling a couple more of the harder problems to section 1.1. And this is something that I'm going to do for every section. I feel like a lot of times when you're browsing through YouTube trying to get help with math, calculus in particular, a lot of the easier problems and more basic problems are covered, and like everyone knows how to do those, they kind of show you how to do them. But a lot of times when you have the harder ones in the section, you don't really have any sort of help online. And so hopefully I can do a service to you guys and tackle some of the harder ones. And so in this video, we're going to be doing problems 32 and 34 for section 1.1. And these, and I'm sure you'll be able to tell, are going to be a little more of a step up from what we've done in the past. And so in this problem, 32, we have this piecewise defined function. So we have let f of x equal to negative x squared if x is less than 0, the tangent of x if 0 is less than or equal to x, or less than pi halves, and then the ln of x minus pi halves plus 1, weird function, eh? If x is greater than or equal to pi halves. So we have this function, it's probably going to have some sort of weird shape, probably have some cutoffs, whatnot. And then here it says A, sketch the graph of f. B, find all values of x in the domain of f at which the limit of f exists. C, find all values of x in the domain of f at which the left-hand limit of f exists. And D, find all the values of x in the domain of f at which the right-hand limit of f exists. So these three are basically asking for the limit, the whole limit first of all, and then finding which values of x the limit exists for, and then the left-hand side and the right-hand side. And then we're going to talk about how that can change based on, because the limit might not exist at a certain point, but the left hand might exist because it can possibly approach a finite value at the left hand side, but it might approach an infinite value at the right hand side, so that the whole limit and the right hand limit might not exist, but the left hand limit might exist, or something along those lines. So the first step to this problem is to graph this function, because this is one of those things that you can just kind of see graphically. And besides, part A, we have to sketch the graph anyways. They're probably just leading us to find the easiest way to do these last three. So here, let me just create my xy plane, and we're going to draw this up. Might need a little help from our friend Desmos for the last part, and I'll show you why. So this is going to be y, and this is going to be x. Alright, so but these first two parts are pretty straightforward. This is one weird function, but this one right here, negative x squared if x is less than 0, right? So at this point 0, and let's say you plug in 0 right here, 0 is going to be 0, right? So this point would be as part of this function, but since it's not, I'm going to put a hole right here. But then it says negative x squared if x is less than 0, right? So you know that if you were to do x squared, it would go up like this. But since it's negative, it's going to be all these negative values, so it's going to go down like that, right? So it's going to look like this. Cool. So the function looks like that as you go from negative infinity all the way to 0. And then it's going to be tangent of x if x goes from 0 to pi half. So it includes 0, right? And then it goes all the way to pi halves but does not include it. And so let's look back on our trig days, right? So I'm going to just put this side note over here. So remember the sine function, right? It went like this, went down, went back up, and this point right here is pi, and this was 2 pi, right? And so that's going to be one full cycle of the sine function. And then you probably remember the cosine function looked a little bit different. It just kind of, this whole thing shifted over pi halves. It's going to start up here, it's going to go down, it's going to go up like that. And so this point is going to be pi, and this point is going to be 2 pi. That's a cosine function. And remember, the tangent is going to be the sine over the cosine. So you take all these values, and then you basically take the quotient of them. And let me get this out of the way first. Delete. And it's going to give you something like this. The tangent function. It'll go like this. And then you're going to have these asymptotes. Remember, the asymptotes are just these vertical lines that the function cannot pass through. And it's going to approach the value where the asymptote is going to go closer and closer and closer, but it's never going to quite hit. And then there's going to be this asymptote right over here. And then your function is going to look like this. So this point right here is actually pi halves. And then this point right here is negative pi halves. And then you probably remember that the cotangent is going to look like this, except it kind of goes like that. So it goes the other direction. Because if you think about it logically, the cotangent is just the inverse of the tangent. So it makes sense. So this is our tangent, right? And now let's use this. And obviously, you don't have to know this. It's a good idea to know trigonometry to do calculus anyways. But if you're not super solid, I would say go ahead and review it. Or one thing that you could even do is you can just plug in points and kind of see the main trajectory. You could even do that. I just like to use this because it's a little bit easier. Because now that we have this, we can actually apply it right here. Because it says tangent x if x goes from 0 to pi halves. And it makes sense why it stops at pi halves is not included, because in the actual graph of the tangent of x, it cannot equal to pi halves. Because if you think about it logically, and I like to think about everything logically, I'm sure you can tell, if you think about the unit circle, so if I were to draw the unit circle like this, pi halves is going to be this point right here, right? Right? Because this is pi, this is the half of it, so this is going to be pi halves. And if you think about the values of sine and cosine, what is the sine value, the y value? It's going to be just 1, right? And what's the cosine value? It's going to be 0. 0 or 1. And what is tangent? See, tangent of x is equal to the sine of x, right? Sine of x over the cosine of x. And in our case, that's going to be 1 over 0. But you can't divide by 0, so it's undefined. And that's why there's an asymptote here, because it can never equal that value. It can get really, really, really close, but it can never quite hit. So let's use all this that we know, just a little review of trigonometry, and then let's apply it over here. So the first thing I'm going to do is I'm going to create a little asymptote at pi halves, right? So this is going to be pi halves right here. At this point, all right? And then we're going to have this sort of upward trajecting parabola. It's going to go all the way up, but never quite hit. It's going to go like that. And that's a pi halves. But one thing that we're going to have to change, see how x goes from 0 and it includes 0. So there was a hole originally, but we can actually fill it up. And basically how domains work, and you might have learned this from pre-calculus, is that when you go through this one part of a piecewise function, and you have a hole here, but then you go through another part, and it's actually filled in, that actually overrides that hole. So we can actually fill this in. So it's going to look like that. Perfect. So that's that part. And now we just have this last part. The ln x minus pi halves plus 1 if x is greater than or equal to pi halves. So here we have this value. So it's actually equal to pi halves at this value. But this is one weird function, right? So the first thing I'm going to do, first of all, is I'm just going to delete all this stuff. That didn't work. I don't want to delete that over there. I'm going to delete that. Just being careful not to delete the other stuff, right? Delete. I want to delete this over here, just to kind of create some nice room for what we're going to do next. Okay, and now we're going to go to our friend Desmos right here for some help, because this is one of those functions we could easily graph the other two pretty easily just by looking at it, but this one's kind of weird. So what I'm going to do is I'm going to go to Desmos and then put this function in and then plug in different values past pi halves and see what numerical values we can get. That way we can draw a graph. And so here we have the ln of x minus pi halves plus 1. Let's go to Desmos. I'm going to go to ln of x minus pi halves plus 1, right? So they're going to look like that. And now, remember that value where we could go to a table? This is actually going to be very, very useful. I guess we could even look at this graph just like this if we wanted to. But I'm going to show you how to do it in a table as well, so you can kind of see both. So here, convert to table. And remember, it starts at pi halves, right? So I think one thing that would be good to know is see what is the value when it's at pi halves. Pi halves, it's going to be 0. Okay, good to know. How about another value? Remember, pi halves is halfway across, halfway to pi. So what's our next value? How about 2 pi over 3? That's a good one to know. Okay, and next one would be 3 pi over 4. I'm just kind of going as far as the next ones along the unit circle. And then I'll do one more. 5 pi over 6. Actually, 2 more, because then I want to find out what it is for pi. I might not use all these values, but it's good to have more than less, I guess. 5 pi over 6 is going to be that. And let's do pi. Alright, so we have all these values right here. Obviously, we could just look at the function right here. It's pretty chill. But it's always good to know what all these different values are. And that way, when you go over here to your function, and we know our graph is going to look something along the lines of this. It's going to go something like this. And it's going to even out right here. But then we can put in our actual value. So we have pi over 2, right? Then we have 2 pi over 3. Then we have 3 pi over 4. We have 5 pi over 6. And then we have pi. Alright, and let's go over decimals again and see what those values are. So for 2 pi over 3, well, first of all, 0 for pi over 2. I'm just going to do it to 2 decimal places. Actually, just 1. Why not? 0.4, then 0.6, then 0.7, then 0.9. Let's bring that over here. So we have this. 0.4. Now this one right here, 0.6. Then we have right here, 0.7. And the last one, where it's pi, is going to be, and it doesn't fit, I just don't have room for all these numbers, 0.9. So those are our values for that. And that's what our function looks like. Obviously, we probably didn't need to go overkill here, just seeing the trajectory of how the curve goes. But it's always good to know to just be able to plug in values, and that's the way you can sketch the graph. So that's it. Sketch the graph of f. We did it from negative infinity all the way over here to positive infinity all the way over here. We did it. We sketched the graph, so part A is done. Now we have part B. So this is the part, so these last 3 problems are actually, I'm going to go through them pretty quickly because it's not too complicated. Sketching the graph, I would say, is probably the most complicated part of this problem. But with part B, what you do is you really analyze this graph and kind of look at logically what happens. And so B, it says find all the values of f in the domain, find all the values of x in the domain of f at which the limit of f exists. So remember, when a limit exists, we know that first of all there has to be a continuous function, right? Because if there's not a continuous function, you can still have a limit existing, but only with certain properties. And that, like, remember you had the hole in the last problem? And so here, let's look at the domain. So the domain, well, first of all, let's talk about what is the domain of this function, right? So it's going to be defined all the way through here. You can always find a value. And then at this value of pi over 2 is actually undefined, right? Because here it goes all the way up here, and here you have a value, but it's going to keep going up there. And so let's talk about the values in the domain of f at which the limit of f exists. So we could say that the limit is going to be existent for every part of the domain, but so every value other than pi halves works. But let's think about this value of pi halves. See, on the left-hand side, it goes all the way to infinity, right? And on the right-hand side, it goes to 0. And those values are obviously not the same. So we would say the limit does not exist, and I'm going to write this. The limit, as x approaches pi halves of f of x, does not exist. But would you agree with me when I say that it exists for every other part? So it says, what are the values of x? Let me use interval notation here. I'm sure you've seen this before. So we would say it goes from negative infinity to pi halves. And here we're not going to use a bracket because it doesn't include pi halves. We're going to use another parentheses. Union, because there's this other part, and it's going to go for pi halves again with a parenthesis because it's not included, pi halves, and then all the way to positive infinity. And that's it. That's the answer to B, because it's going to include, the limit's going to exist for all these values. It's not going to be included for the value of pi halves, but literally every other value in existence it is. So there it is. That's B. And how about C? So C and D are interesting because it says find all values of x in the domain of f at which the left-hand limit of f exists. So we know the left-hand limit, just kind of the process of what's greater and what's less. The left-hand limit is going to exist for all values that the whole limit exists for, because the whole limit basically says the left-hand limit and the right-hand limit exist and go to the same value. So technically speaking, it's going to be at least all this, but could it possibly be more? And so here, we're going from negative infinity all the way here. So remember, for this one, there's only one value in existence that it does not work for, and that's the value of pi halves. So let's evaluate that value, and let's see, does the left-hand limit exist? So we're disregarding this entirely. The left-hand limit goes all the way to infinity, but since it's an infinite value, it's not an actual real number, it does not exist. So here we're going to have the limit of x goes to pi halves minus, because it's approaching from the left side, of f of x does not exist. So I'm going to write does not exist. And then we would also say that using interval notation, it's going to be the exact same domain. It's going to be negative infinity, pi halves, union, and then pi halves, infinity. And that will be it for that. And let's do part D now. Find all the values in x in the domain of f at which the right-hand limit of f exists. So this one's interesting, because here we're not going to evaluate the left-hand part, and we know by default it has to at least include this, right? So again, we're evaluating just that last part, that pi halves, but we're not looking at the left-hand side at all. We're looking at the right side. And see, the right hand, it goes to this value of 0. So it actually would include it. Does that make sense? So it includes every other value, and also it does include pi halves because it goes to that one value, and it actually is a finite value. So we would say that the limit as x approaches pi halves from the right side, so plus of f of x, it actually does exist, and it equals 0. And then we would also say, what is the interval? And the interval goes from negative infinity to positive infinity. Another way you can write this is going to be in the range of all real numbers. And that's it. So we found B, C, and D. We found the intervals for which the limit does not exist. And that's basically how you find that. And obviously this problem, you would say, is a little bit harder than some of the others, but I want to do this problem just to kind of show you how you can do it, and that it's not really that complicated. So that's 32. Let's do 34 now. All right. So 34, we have the square wave function. So it's a function that looks like this. It says the square wave function f can be expressed in terms of the Heaviside function as follows. So it says f of t equals h sub k of t minus h sub k t minus k plus h sub k t minus 2k minus a. So it's going to be this plus minus sort of alternating function. Minus h sub k t minus 3k, and then another plus h sub k t minus 4k. So you're going to see that it has this t minus nk, and that constant of k is going to be added by 1 each time you go through it, and it's going to be alternating. And that might sound like a whole bunch of math mumbo jumbo, and that's why it might be easier to look at the picture. I'm myself a bit more of a visual person, so I like seeing these things. So you see here, at this value of 0, starts k, then it goes all the way to an x value of k, and this dot right here means that this actually does not exist. It goes here, like disregard these dotted lines, it goes here, and then goes here, then goes here. They just find this way to kind of sort of connect them, but they're not really connected. It's just that, like, logically you can't connect these two lines mathematically. And so you have this line, then you have this line, then you have this line, you have this line, then you have this line. And it basically says, referring to the following figure, show the limit of t as it goes to nk. So remember, here we have y and t. That's why it has t instead of x. T goes to nk. So not just k, not just 2k, not just 3k, all the way up to nk of f of t does not exist for n is equal to 1, 2, 3, going on forever. So the best way to do this is using a method called generalization. And technically this is a proof, which is kind of interesting because you don't do proofs too much in calculus. That's more classes like linear algebra, discrete math, if you ever take abstract algebra, stuff like that. But here, you're going to start with this value of 0, and then as it goes to k. So the best way to do this is just kind of look at it in generalization. You look at the first few values, and then notice a pattern, and then you can assume that pattern for forever. And so let's approach the value of k first of all. So what is the limit st goes to k? So this is going to be 1k. Maybe I'll write that. T goes to 1k. So it's going to be this value right here. So let's evaluate it from both sides, right? Let's do negative side first. So what is negative side of this f of t? I'm going to write that. F of t. So looking from the left side, right, it's going to go all the way, and it's going to keep approaching k, right? It's not changing at all. It keeps approaching that value. It's just a straight line, right? So this is going to be equal to k. And what about the limit? I'm going to do this on this other side. The limit st goes to 1k from the positive side of f of t. Okay? And here, this dotted line doesn't matter at all. You're just going to go here closer and closer and closer to 0, right? And it doesn't ever change. So here you're going to have this value of 0. And so you have this k, you have this 0, but they're different values, right? And we already know that if the limits go to different values from both sides, then the limit does not exist. So you would say the limit st goes to 1k of f of t. There we go. It does not exist. So I would say D and E does not exist. So that's for that one value, right? And now let's look at it for a second value. How about the limit t goes to 2k, right? So now we're not looking at this point, we're now looking at this point, right? So it's a little bit different, but one thing I would venture to say is actually not that different. So let's look at it from the left-hand side and from the right-hand side again, right? So let's look at it minus f of t. So what happens when you approach it from the left side? Well, if you go from the left side, you start here, get closer and closer and closer to here, you get to 0. It doesn't really ever change. So that's going to be 0. Pretty easy, pretty simple. And now, let's approach it from the right side. So we have the limit st goes to 2k from the right side. And what happens when you approach it from the right side of f of t? Well, looking from the right side, you get closer and closer and closer to this value, and it's k. It doesn't really ever change. So here you're going to have k, and you're going to say the limit st goes to 2k of f of t does not exist. The exact same value. The only thing that was different between these two examples is that the left-hand limit and the right-hand limits were swapped. But that's pretty much it. And so let's just do one more example, but I'm sure you can kind of see the pattern here. So let's do the limit st goes to 3k. So here we have the limit st goes to 3k. And let's approach it from the left-hand side. So here we're analyzing this point. And here we're going to have f of t. And as it approaches it from the left-hand side, it's going to be this value of k. So see how this, it just kind of swaps, right? And this is just going to be equal to k. And looking at it from the right-hand side, it's just going to be equal to 0, right? So the limit, it's always good to just write the notation. A lot of times because I tutor math as well, and I've helped a lot of my students, and what's interesting is they just do these problems where they're just putting these numbers, and they know how to solve limits, but it doesn't really help because me looking at it, and especially a teacher looking at it, they don't really know what the number represents. So always write the correct notation. Always good to do. So limit st goes to 2k from the right-hand side of f of t is going to be equal to 0. you'll notice that this is the exact same values that we have for the first one, and that's basically because it's in the exact same position. So now you have these three values, and here's where the generalization comes in, because we have to show the limit for nk does not exist. But see how this pattern goes, and it continues on and on and on. And you can actually say, just generalizing, so generalizing, we can say that the limit as t goes to nk, and here, notice that we're not doing the left-hand side or the right-hand side, because those do exist. But when you put them together, since there's different values, and that's never going to change as far as we go, right? Of f of t, almost forgot that part, does not exist. And that's pretty much it, because we found that going through these first three values is going to follow the exact same pattern, and we've already covered all the different scenarios that could possibly come up. And so therefore, that limit does not exist, no matter how far you go. So those are the two problems. Those are a little bit more on the complicated side. Hopefully those were helpful. And in the next video, we're going to go to the next section, section 1.2, where we're going to learn a little more different methods to solve limits, things that will help us a little bit more on that skill. All right, see you next time.